So in this slide, I would like to share with you a few examples of use of the Bernoulli equation. So the first application, we call it as a free jet. So a free jet means we have the fluid flow, the liquid move at certain velocity in the atmospheric pressure. So means the free means it moves freely in atmospheric pressure, because we assume that the atmospheric pressure is equal to 0. So if a flow of fluid moving in atmospheric pressure, so we call it as a free jet. So to create a free jet, so there is a few ideas. So the simple one is, for example, if we have a tank here, so and then we make a hole at the bottom surface and water will flow at certain velocity. So we call this phenomenon as free jets. So or you just make a hole at the vertical wall here, so the water will flow at certain velocity. So also free jet is if you open a pipe, so let's say you have a pipe here, so water comes out, this is also called a free jet. So means that water move at certain velocity in atmospheric pressure. Normally we are calculating as pressure gauge, gauge pressure, so means that the atmospheric pressure is equal to 0. So and then how to evaluate this one? So let's say we have this condition. So we have a tank like this one. So and then water fill until this level. So and then at the bottom surface here, so we have a hole and then water flow at certain velocity. So first thing first, you need to draw the datum in your diagram. So let's say normally people will take this surface or this level is the datum, because this is the boundary between the fluid inside the tank and fluid that move outside or move in the atmospheric pressure. So and then here we could draw a distance h here, mean the distance from the point where the fluid comes out until the free surface of the liquid. So and then to use Bernoulli equation, we must determine the streamline. So you just imagine that we have one molecule from the free surface here. So it starts with 0. So means that if the hole here is closed, so this molecule is equal to 0, the velocity of that molecule. And then when we open this this hole, so this molecule, so it start to move, because it start to fall down. So and then this molecule from velocity equal to 0 start to have a velocity, and then it will go through the hole here. So let's say this is point number 2 for this molecule. Okay, so and then the second step is try to determine all the parameter for point number 1 and point number 2. So you know that we know that the Bernoulli equation is P over rho g plus V square over 2g and plus z. So means try to determine what is the pressure, the velocity and the z. So at point number 1 here, so the pressure 1 is equal to P atm and it is equal to 0. So and then velocity 1 here, so as I said, it starts from the static condition and then it moves with certain velocity. So means that the velocity at point number 1 is also 0. So and then we have Z1 here. So Z1 means the potential energy. So the potential energy needs to be measured from one specific datum. Fixed datum means datum for point 1 and point 2 must be the same datum. So it is okay for us to take this line as the datum. So mean the Z here is h. So it's equal to this height. So next, in point number 2 here, again, please list down all the parameters. So let's say P1 here. Okay, and then P1 here, we assume that because the molecule is now free, its flow or it's moving in atmospheric pressure. So atmospheric pressure, so it is equal to 0. So P ATM, it is equal to 0. So I'm sorry, P2 here. So V2 here. So velocity at point number 2 here. So for sure, it's fluid move at certain velocity. So velocity 2 here is unknown, means it moves at certain amount of velocity. So and then Z2 here, because this point is at the same at the starting point, it is on the datum, so the Z2 here is equal to 0. So this is all the parameter that we need to substitute into the Bernoulli equation. So it is okay for us actually to take different datum. For example, if you don't like to take this datum and then you want to take point number 5 here as your datum. So it's still okay, your calculation is still correct. So let's say we take this is the datum. So means that if the datum is 0 and this is the positive side, so means that the H here must be H plus capital H. So and then the H for Z here must be H. Okay, so it is not 0 anymore because the height is measured from this new datum. So you need to be very specific where is your datum. So and then if you're not satisfied with this datum, it is okay for you to change with another datum. For example, if you want to change the datum from the free surface, so let's say this is our datum. So let's say this is our datum. So because we are measure downside like this one, so means that it is a negative side. So means that the datum of Z here, Z1 here is not H plus H, so it will become, okay, for Z here, so for Z here, Z at point number 1, because it is on the datum, so Z1 will become 0. So and then for Z2 here, okay, for Z2 here, so because it is at this point, so we need to mention as negative H. Because the value is H, but it is below the datum, so we give a minus sign for H. So and then after we substitute so let's say we have the Bernoulli equation P1 over rho G plus V1 square over 2G and plus Z1. It is equal to P2 over rho G plus V2 square over 2G and plus Z. So we assume that Z2 is 0. So V1 is 0 and Z here is H. So and then pressure is also 0, but because both of the condition is exposed to atmospheric pressure, now we only have V2 square over 2G is equal to H. So we could simplifying we could calculate the value of velocity here. So velocity 2 is equal to square root of 2G and H. So as I mentioned here. So this idea is introduced by one scientist called Torrecelli. So the idea of V equal to square root 2GH is sometimes called as a Torrecelli theorem.